Okay, remember how back in chapter 4, one of the things we talked about was right triangles and how the sides of a right triangle were related in certain ways relating to the trigonometric functions of the angles. Like, for example, the sine of an angle of a right triangle was equal to the opposite side over the hypotenuse. So we used SOHCAHTOA to figure out the missing unknown sides or angles of a right triangle. Now we're coming back to triangles, but we're not limiting ourselves to just right triangles. We're going to look at some things that we can do with any triangle, even if it doesn't have a right angle. And so the thing we're looking at today is what's called the law of sines. So the law of sines says if ABC is a triangle with sides little a, little b, and little c, and the way that works is little a stands for the length of the side that is across from angle A. Little b is across from angle B, little c is across from angle C. In that case, little a, the length of that side over the sine of angle A is equal to little b over the sine of angle B is equal to little c over the sine of angle C. So really that's kind of three equations in one. A over sine A equals B over sine B, B over sine B equals C over sine C, and then C over sine C is equal to A over sine A. And that works with any triangle. To show you why it works, first picture a triangle that's set up this way with the side from A to B on the bottom. So it's resting on side AB, which is opposite from angle C. So angle C is at the top. And then imagine drawing a straight line down from C, that particular vertex of the triangle, down to the bottom, perpendicular. And that divides the whole thing up into two separate right triangles. And because those are right triangles, we can do our SOHCAHTOA thing on them. So if you look at the triangle over on the left here, the one I've got shaded in blue, here's angle A, and the sine of A is equal to the opposite side, which I've got labeled H, the height of the whole thing, over the hypotenuse, which is B. So the sine of A equals H over B. Now look at the other right triangle, the one that is actually on the right. So the sine of angle B is the side opposite from that, which is also H, over the hypotenuse of that triangle, which is A. So sine of B is H over A. Now, H then is equal to little b times the sine of A, but it's also equal to little a times the sine of B. So those two things, since they're both equal to H, they must be equal to each other. And then dividing both sides of that equation by the sine parts, you get that A divided by the sine of A equals B divided by the sine of B. So that shows that little a over the sine of A equals little b over sine of B. To show the rest of it, like that little b over the sine of B equals little c over the sine of C, you just turn the triangle around so it's resting on a different side and go through that same procedure. But what I've done so far assumes that when I drop a perpendicular from C down to the base of the triangle, that perpendicular is inside the triangle, which is what happens if A is an acute angle. But what if A is an obtuse angle? Then if you start at vertex C and go straight down, then that line that we've labeled H for the height of the triangle is outside the triangle. And the two right triangles that you have to play with, well, one of those is completely outside the obtuse triangle that you were really interested in. So if you're messing around with that, trying to say, okay, the sine of A equals H over B, that works for angle A being the angle I've got marked here in red. But as far as the triangle is concerned, angle A would be the angle I've got marked in blue. They're two different angles. But that's not really a problem because those two different angles are supplementary angles. Together they add up to 180 degrees. The one I've got marked in red is an acute angle in quadrant 1, and the one I've got marked in blue is an obtuse angle in quadrant 2, but they have the same sign. Every angle in quadrant 1 has a corresponding angle in quadrant 2 that has the same sign, and those two angles together are supplementary. They add up to 180 degrees. Like, for example, 30 degrees and 150 degrees both have their sine 1/2. Sine of 30 degrees is 1/2, and the sine of 150 degrees is 1/2. So because these two angles have the same sign as each other, the same little argument still applies. And this fact about supplementary angles having the same sign as each other is going to be important coming up in a little while. So now let's look at some examples of this law of sines in action. And it's easy to remember because of the nice pattern everything falls into. So let's say we have a triangle and we know that side A has a length of 12.2 centimeters or miles or whatever unit you're working with. Angle A has a measure of 37.1 degrees, and angle C is 76.6 degrees. So we know one side and two angles. And we want to figure out, okay, what else is going on with this triangle? What's the other two sides and the other angle? So we know little a, big C, those are three of the four things that we can put together in this law of sines relationship. We can fill in the numbers for little a and big C and work out from that what little c has to be. So if we do that, 12.2 over the sine of 37.1 degrees equals little c over the sine of 76.6 degrees. Then sort of cross multiplying, 12.2 times the sine of 76.6 degrees equals little c over the sine of, or times the sine of 37.1 degrees. So little c is 12.2 times the sine of 76.6 degrees divided by the sine of 37.1 degrees. And making sure you have your calculator in degree mode when you calculate this, it should come out to be something that when you round it to the nearest tenth, and I'm just going to be giving all my answers rounded to one place after the decimal point here. When you round to the nearest tenth, you end up with 19.7. So now we know little c. What we still have to find would be little b and big B, the side and the angle. If we don't know either one of those, how can we set up our law of sines to find them? Oh, well, remember, with any triangle, all three sides have to add up to 180 degrees. So if you know two of them, you can work out what the third angle is. So in this case, angle B is 180 degrees minus 37.1 degrees for A, minus 76.6 degrees for C, and that comes out to be 66.3 degrees. And now that we have a measure for angle B, we can fill everything into the law of sines and work out what little b is, and it works out to be 18.5. By the way, if you've done everything correctly, the longest side should be across from the largest angle, and the shortest side should be across from the smallest angle. So if you arrange angles A, B, and C in order of size, sides A, B, and C should also be in that same order. Okay, this was a pretty straightforward example where you have two angles and one side. You can also use the law of sines when you have two sides and one angle, but things get a little bit more complicated there. And so I will end this video right here and pick up in part 2 some examples of that and what can happen there. See you then.